Selecting the right TVS device protection for a system is very difficult because the TVS device is designed with various parameters, such as breakdown voltage and dynamic resistance, which may or may not work well in concert with the chosen ASIC to meet the desired system-level robustness. One TVS device might provide good protection with an older ASIC but perform poorly with a new version of the same ASIC. The question remains, why did the ESD protection fail to protect the ASIC? Because the TVS vendor does not know anything about which ASIC it will be protecting. A TVS device is characterized on the datasheet in the one way that it will never be used by itself. But when we put a TVS device in a system, then the interaction with the ASIC is critical. Here we see a current reconstruction scan which shows the residual current that passes through the system to the ASIC past the TVS during a zap on an I/O pin. Again, if we watch it, we see the current flow into the TVS and then also some residual current flows into the ASIC. The residual pulse is the critical element that we have to understand. How is the current shared between the TVS device and the ASIC? While we often hope that the TVS will shunt most of the energy, how do we know if the ASIC can survive the rest? Consider this simplified example. Suppose we have two TVS devices being tested to protect the same ASIC. TVS A, the device under test, or DUT, shunts about the same amount of current as the device under protection, or DUP, and so it quickly reaches its maximum limit, and the system fails, at about 4 kV. We can see that if TVS B can absorb a higher fraction of the current and energy, then the system overall can withstand a higher IEC level without allowing the ASIC to reach its failure limit. Therefore the system passes at a higher level, perhaps 6 kV or more. The way the DUT and DUP devices interact is dynamic, and it can be analyzed by the test methodology called SEED. SEED is a system-efficient ESD design methodology introduced by the ESD Industry Council. It requires information about the device under protection in the form of a specialized ESD SPICE model for simulating high transient currents, which is substantially different than an IBIS model for signal integrity. The current sharing between the two devices is critical, and we can simulate it with the PESTO SEED simulation tool, and carefully pre-validated models. This system provides a simple platform to select different TVS devices. Here we will try the ESD 122 and 224 from TI, and a diode's DT1452. These are modeled from manufacturer-provided data, or third-party measurements. For the ASIC we'll choose an SD microcontroller here and run it. The simulator will create hundreds of seed simulations in order to find out what level the system can survive based on the current sharing at different levels, essentially just as you would do physical step testing in the lab, but without the time and expense. Here we find that the diode's part performs a little bit better at the system level than the other two devices, which provide about 4 to 4.5 kV of system robustness, versus 6 kV for the other part. In this edition we can look at the actual current and voltage transient plots for this device on the left versus the ASIC on the right. Here we see a residual pulse of 2.7 to 3 amps at 5.5 to 6 kV, and beyond that, the ASIC device will fail. Meanwhile the TVS device is shunting about 9 or 10 amps at 6 kV. So although this TVS device may survive up to 16 kV by itself according to the TVS manufacturer, the resulting residual pulse will cause the device under protection to fail. To try it yourself, go to lite.pesto.design and sign up for a free account and start solving your ESD robustness problems right away. Thank you for your time.